Right, back in the saddle with some more quantum mechanics. So, when we left off talking last time, we were concerned with experiments that showed the weird nature of a light, right? And we were dealing with light the whole time. And and then we ultimately came to this idea where we were dealing with the interaction of light and matter, and we were ultimately showing then that that light had this quantized nature to it, and that oscillating dipoles produced this light, and each frequency of light had set amount of energy associated with it through the relationship with the Planck's constant h. All right, and so then we went ahead and we moved forward and we look at Planck's the Planck hypothesis, and that was the quantum hypothesis ultimately, that every frequency of light has some minimum amount of energy that must be there for that light to exist, and it's related through some whole number integer multiplied by this constant, this h constant, and that h ultimately gets derived from fitting the experimental data, right? As you fit this data, you need to change whatever this value h is, and that h ends up being the constant, Planck's constant, right? And so you go ahead and that'll fit all of these curves, and it'll fit any black body. And so we left off talking about black body radiation. And so now what we're going to do is we're going to talk about some other classical experiments that start to set the stage for the quantum nature of matter, not just the quantum nature of light and or energy. The photoelectric effect. So this got Einstein the Nobel Prize in 1906, and it was kind of a big deal. So let's take a look at it. So Henrik Hertz in 1886 runs a series of experiments, and what he sees is he finds that electrons are emitted upon radiation, are emitted upon irradiation of a metal surface. So imagine there's some metal surface, right? And we shine light on it. And what he says is, he says in these observations that the ejected electrons ultimately have some kinetic energy, right? That kinetic energy is equal to 1/2 mv squared. And so they shine light on this metal surface, an electron pops off, and it's got some velocity associated with it. Okay, and that velocity, because the electron has some mass, gives it some kinetic energy. All right. And Henrik, like I'm buddies with them, Henrik Hertz ultimately says that this thing's going to be called the photoelectric effect because it's going to involve photons and electrons, right? And he didn't name it that, actually. It gets named by Einstein as the photoelectric effect because Einstein invents this concept of photons about 30 years later, 20 years later, excuse me. So what does this apparatus look like, right? So it's kind of important to understand what the heck the apparatus is. So here's the apparatus. So what Hertz made was he made something called a spark gap. And so you have metal on this side, and you have a slight potential difference across here where this would be positive and this is going to be negative. And what he does is he shined light on this metal surface. And now this spark gap's not that big. It's very small. It's a very small jump, right? And so he shines light on here. When he shines light on there, electrons are ejected, and they're attracted to the positive electric field coming off of this side. All right, and so that's the game he played. And he varied the voltage down here of the potential, and you could ultimately reverse that voltage, and you could stop the electrons from coming across. And based on the relationship between wattage and the charge, you could establish what the kinetic energy of these electrons are. And so that's how we established what the kinetic energy of the electrons were coming across this gap, by varying the voltage down here. And he could also vary the frequency of light being emitted onto this metal surface. And he could also vary the intensity of the light, right? He could make it brighter or dimmer, and he could change the frequency. And so what did he see when he varied that frequency with respect to light? Well, you got to remember at this point in time, there was no concept of a photon, but there was this corpuscle kind of idea, right? That got brought about by Newton, where he said, look, light has these is made up of these corpuscles, it travels with infinite speed, so on and so forth. So there is kind of this idea bouncing around in the physics community, but there's no real hard evidence for this yet. All right, so moving forward, when Hertz runs these experiments, he sees some things that differ from classical wave theory of light, right? Because people are arguing it's a particle, no, it's a wave, it's a particle, no, it's a wave. Okay, well, from the wave theory of light, classically, we would think that the kinetic energy of the electrons that are emitted, right, these electrons that are kicked off, that kinetic energy should increase linearly with the light intensity regardless of the frequency that you've shown on the metal surface, right? So I have light coming in, doesn't matter what the frequency is. According to classical theory, there's more energy if the intensity is higher, right? Okay, well that makes sense. There's more, as we understand intensity, that's photons per unit time, right? And so clearly there's more energy coming in. But what they saw, so classically, the kinetic energy of the electrons should increase with the intensity because I'm adding more energy to collide with this electron or couple with the electron in order to get it to spit up really fast, right? But experiments showed something different. It showed that the kinetic energy of the electron remained flat with respect to intensity at a given frequency. So experiment shows that my kinetic energy of the electron never changes. Doesn't matter how bright I make the light or how many photons I shoot at one time, the velocity of my electron is going to be the same. And they didn't understand back then that each photon, only one photon couples to one electron at a time. They just thought that the light was this wavefront, and if I had more of this wavefront, then I would impart more energy on the electron. But that's not the case, right? The next anomaly that they saw with respect to classical ideas and theory was that the kinetic energy should remain flat with respect to the frequency, and it should only depend on the intensity, right? So what they expected classically is that the kinetic energy of the electron with respect to variation of the frequency should remain flat. That's what classical understanding was. But what they actually saw was that past some threshold frequency, nu sub naught, right? So past some threshold frequency, the kinetic energy of the electron increased linearly with increasing frequency. That's a wild idea to them, right? Because how could that be? I'm not giving any more energy to the metal, they thought, by increasing the frequency. I need to increase the intensity, right? Which ultimately is, photons per second, but they didn't understand it as such back then. All right. So that's a pretty interesting idea. So if I have, say, potassium, right? I have potassium here, and it's got a ionization potential of 2.0 electron volts, and or we could call this a work function of 2.0 electron volts. And that's how much energy is needed to separate the electron from the potassium nuclei, right? Okay. And so if I go ahead and I shine 700 nanometer light on there, which has an energy of approximately 1.77 electron volts, and it couples to the electron in this metal, in the electron gas surrounding this metal, that electron doesn't come off. It doesn't fire off into space because there's not enough energy to overcome the ionization potential. But if I go ahead and I shoot 550 nanometer light at our metal surface, which has an energy of approximately 2.25 electron volts, which is greater than our work function or ionization potential, it'll fire off an electron. And that electron that comes off is going to have some velocity associated with it. Now, if I go ahead and I shoot even higher frequency light at my metal, right? Shorter wavelength light, higher frequency, higher energy, right? it's going to couple to that electron, and that electron that pops off is going to come off with even more speed, right? It'll have a higher velocity than it does from the lower energy light. And this was really quite mind-blowing to Hertz. And after he did this experiment, he left it alone. 1886, he does the experiment, never looks back at it. He leaves it to the rest of the physics community to sort it out. So Einstein comes along in 1906, about 20 years later, and he says, okay, look, I'm going to extend Planck's quantum hypothesis. I'm going to extend this idea. And we're going to redefine light, and we're going to kind of use some ideas from Newton. And he says, look, light's going to be comprised of photons. This is light particles with no rest mass that travel at the speed of light, 2.99 times 10 to the 8th meters per second. Where Newton said that light was comprised of corpuscles that travel at infinite velocity and had no mass, Einstein just takes it a little bit further and says it has some finite velocity, and instead of calling it corpuscles, he calls it photons. And he says, look, each photon has some quantized energy associated with it based on the frequency of the wave associated with the particle. Now, this is kind of a really crazy idea because he's saying it's a particle, but he's saying it's a wave. And so effectively, it's a wavicle, right? It's both things. All right. So he then goes on to say that the energy and momentum of the light is related to the frequency of the photons via the Planck hypothesis that says E is equal to the Planck's constant times the frequency. And he says that the momentum also has a relationship to it. And he says that that is Planck's constant times the frequency of the wave divided by the speed of light. All right. So therefore, if the light's frequency is larger, there's more energy contained in the photon that couples to one electron. So that was really mind-blowing ideas in the 1900s, right? In the early 1900s. So, yeah, man. Thank you, Einstein, for figuring that out. So now, the kinetic energy of the ejected electron is ultimately proportional to the energy of the incoming photon minus the energy needed to remove that electron, right? So the kinetic energy of our electron, right, which is equal to 1/2 mv squared, is ultimately equal to the energy of the incoming photon minus the energy that it took to remove that electron from the nuclei, right? Or you could think of this as an ionization potential, but it's called the work function in this particular instance. And now the work function is just going to be the minimum frequency, nu naught, that's necessary to separate the electron from the nuclei, right? So when we look at our surface, right, and if I'm looking at potassium in particular, right, I see that its work function is 2.0 electron volts. If I'm below that, I can't get an electron to pop off because I can't overcome the electrostatic interaction of the electron with the nuclei. But if I have sufficient energy to overcome that electrostatic attraction or that Coulomb energy, Coulomb potential, I can fire off that electron. All right. So now if I look at this expression, kinetic energy is equal to h nu minus h nu naught. This is just a linear expression, right, where my variable is nu, my slope is Planck's constant, and my intercept is the work function. All right, so we could go ahead and we could plot that. Kinetic energy as a function of frequency, where your y-intercept is the work function. So that's pretty cool, huh? All right. So T here is representative of kinetic energy, and it's equal to this value. So in quantum mechanics, T is kinetic energy. All right. So that's the photoelectric effect. And if we go and we look at the ionization potentials of different substances, we see that different substances are easier to strip electrons from, like potassium's easier to strip an electron from than, say, platinum, right? And platinum's a noble metal, And you know that it's very resistant to corrosion, and that's because it has a really high work function and or threshold frequency. Whereas potassium reacts with dang near everything, right? It'll give up an electron to anybody, and it's got a really low threshold frequency or a really small work function. So, uh, you could look at your periodic table and look at the whole left-hand side, and you have a series of metals, and your ionization potential trends will tell you what the work function is and or what the relationship of the frequency needed to eject an electron off of that metal surface would be. So that's pretty cool, right? So you know all this stuff from Gen Chem, but now you see it in a different light with respect to the coupling of light and matter. All right. So as a result of Einstein's work, he establishes again that there's some quantized proportionality constant h that relates the energy to the frequency of light, and that value is ultimately 6.626 times 10 to the negative 34th joules seconds. All right. And so that was Planck's constant. And the fact that it showed up for the black body radiation issue and for the photoelectric effect was quite mind blowing, right? That it's seeming to be this constant that shows up everywhere if we're talking about quantized systems. And so they rename it after Planck after he dies. All right. So Planck's constant is derived from the slope of our kinetic energy versus frequency line. And we notice that the slope of all these lines is exactly the same. And so that is the Planck's constant. All right. So we've talked about light almost exclusively and its interaction with matter. But now we want to talk about matter because, well, we're chemists and we're trying to manipulate nuclear positions and make substances that are useful to us, right? So we got to understand matter. So Einstein in 1906 proposed light had wave-like and particle-like properties, right? He said it was a wavicle. He didn't say wavicle, but that's the word, right? It had particle wave duality. So some 18 years later, de Broglie comes along and he says, look, man, matter's got this same property, not just energy, not just this light, this light thing, whatever this thing is, right? And he says, look, we expect matter to act like a particle, but it can have wave-like properties. And he establishes his hypothesis, and he says, look, the wavelength of any particle is equal to Planck's constant divided by the momentum of that particle, where momentum is equal to mass times the velocity. So he says, look, every bit of mass or matter is oscillating. It's got a vibration associated with it, or it's got some oscillatory sinusoidal nature to it. And he argues that light obeys the equation above such that light of a smaller wavelength carries more momentum, and in turn it carries more energy. All right, so we know that, right? So light of a smaller wavelength, if this is smaller, the momentum is bigger, right? Okay, so it's got more energy. All right, so light follows that. So that had better be true if you're trying to build upon it, right? And then he says, look, it also works for matter, but for matter that's got a large mass, right? If I have a very, very large mass, well, then my wavelength is extremely small and or my frequency is really, really high. So you're not going to be able to observe that wavelength. We don't have an instrument that can measure such a high energy wavelength once the mass gets very large. But if your mass is very small, like that of an electron or a hydrogen nuclei, you can observe the wave-like nature of that particular particle. So with that in mind, experimentalists went out and tried to prove or disprove de Broglie's ideas. And we're going to look at particle generation right now. And before we do particle generation, let's look at X-ray generation. So how do you make X-rays, right? You go to the doctor, they stick you in this thing, bing, bang, bong. there's your picture of your bones, right? But how does the machine work? Well, inside the machine, this is a glass tube, and it's under very high vacuum. And there's a current that's running through a tungsten filament right here. And the game here is we're going to run the current through this tungsten filament until there's enough energy to overcome the work function of these electrons. Then we're going to fire these electrons at a target of tungsten over here. And now what we're going to do is we're going to put a positive charge on this so that the electrons are accelerated towards this tungsten target. Once these electrons strike this tungsten target after they're accelerated, they're going to knock off core electrons, and or they're going to excite core electrons on this tungsten. When those core electrons are excited and then finally decay back down to the ground state, they're going to emit X-rays, very high energy light, because it took a lot of energy to liberate those core electrons off the tungsten nuclei, right, to move them away from the tungsten nuclei. And then when they come back down to the ground state, it emits a lot of energy. Okay, so then you can go ahead and you can focus these X-rays using optical lenses later. All right, Dr. Bo, great. So now we're going to look and see, well, can we play a same game kind of with electrons? Can I use electrons to investigate things perhaps? So if we want to make an electron gun or an electron source, we can look at something called a scanning electron microscope. So here's a scanning electron microscope. And inside this scanning electron microscope is a really high vacuum, 10 to the negative 9th millibar. So there's almost no particles floating around inside this high vacuum. Then what you do is you attach a filament to, and you run a current through it. And this filament is a tungsten filament. That's a single crystal of tungsten. It's annealed and annealed over and over until you get all those tungsten atoms in this perfect single crystal. And then you go ahead and you mill it down to the finest point that you can make, right? And you'll end up with this facet, this tungsten 100 facet. So that's just the symmetry of the crystal that's here. And now look how small this is, 2 microns across right here. So this is approximately half a micron, right? Or whatever that is, half a micron, 500 nanometers, right? So it's very, very small amount of atoms, tungsten atoms at the tip of this probe inside the scanning electron microscope. And so what do you do now? Well, you run a current through this thing. Electrons start to get ejected off this tip. Pew, pew, pew. And these electrons get fired off. They go towards an anode, get focused, right? They get accelerated and then focused through a magnetic lens. And then you can focus them again. And you can go ahead and you can, fire it at any target you want. And it turns out you can focus it much better than you can focus the photons coming out of the X-rays. Okay, great. And now it turns out that the energy with which we expel the electrons can have the same energy as a X-ray, and then consequently, since we know that matter can have wavelengths, right, it'll end up having the same frequency as an X-ray. Whoa, that's pretty crazy, isn't it? So for small particles like electrons or protons, one can observe wave-like properties of the particles via constructive and destructive interference and airy disk diffraction patterns. So imagine I'm firing light through a circular aperture, right? When I do that, I get diffraction and or bending of the light at the edges of our surface. And when that happens, you get constructive and destructive interference, and you'll get something called an airy disk, right? Where the highest amount of intensity is in the center, right? Where most of the light just passes through. And then you will have subsequent rings around that are a function of the constructive and destructive interference of the light passing through the aperture. If you do this with an X-ray gun or an electron gun, like I showed you on the last page, or you do it firing off hydrogen nuclei, you will also see an airy disk just like that. So, I mean, I know I can fire off an electron one at a time, and I know that it's a thing and it's got some mass, so it's a particle, but it displays wave-like properties, which is extremely upsetting to a classical physicist that thought he already understood what the hell an electron was, right? And now he doesn't understand what it is. Okay. So another analogy that can be made is you can make the wavelength of the electron on the order of that of an X-ray. And it'll then act exactly like an X-ray when accelerated at crystalline materials. So imagine I had some X-ray tube. I fire it through a circular aperture. I focus it, hit it on a thin crystal, and my light's going to be diffracted as a function of the atoms within that crystal, right? And I will get what's called a Bragg's pattern or Bragg's diffusion pattern, right? And this is how you do X-ray crystallography, right? It's the game. But you can also do the same thing with an electron beam, right? I can focus an electron beam and I can shoot it through that crystal and I will get the same exact pattern that I see when I use X-rays. Whoa, that is pretty amazing, right? This is aluminum foil, a single crystal of aluminum, and they went and they shot X-rays at it and they shot electrons at it and they get the same exact diffraction pattern. And what's also very unique or interesting is that you can better focus the electron beam such that your diffraction pattern is crisper, right, than it is with the X-rays. So you can get better resolution of your structure within your crystal using an electron beam than an X-ray beam. Pretty cool, right? And so you get really sharp images using electrons. And that's why SEMs and STMs are so great at making images of nanoscale materials. All right. So now let's come to the double slit experiment for electrons. Now, we looked at the double slit experiment for light and photons, but it wasn't until 1927 that they did any sort of experiment that mimicked this double slit experiment for electrons. So Davison and Germer were the first to show that electrons display wave behavior with diffraction patterns of electrons off a smooth nickel surface, right? So this is 1927. So how's this work? So this thing's under vacuum. They have an electron gun. They go ahead and they shoot this electron gun off a smooth nickel surface. The electrons, some are absorbed, but most are reflected off because this thing's already got enough electrons on there. And what they have over here is they have a detector that they can move along, and they move it around and they see what the angle is of the incident beam with respect to where the detector is on this movable slide over here. And what they end up seeing is if in fact the electron's just particles, you would just expect to see a random spread of intensity across this whole region, right? Because it's coming in and it's bouncing off any direction that it's going to bounce off. But what they saw is because this detector moved, they saw different spots of higher intensity as they moved the scanner. And that was due to constructive and destructive interference of the wavefront associated with the electron. Wow. So that's really, really crazy, right? So they figured that out. And what did that look like? Let's see if we can show you what if I save that. So if we look over here to the right hand side, you can see this is the angle of incidence with respect to the voltage that the electron was ejected with. And what you see is this is the intensity of the uh, of the electrons detected at that detector with respect to the angle. And as we change the angle, there's very little intensity, then a lot of intensity, and then the intensity goes down. But you'll notice that the highest bit of intensity is always at 50 degrees, right? It's always at 50 degrees, regardless of the excitation voltage that you start with and or shoot that electron out with. So this proved then that the electron coming out was a wavicle, right? I'm shooting one electron out at a time, but it's interfering with itself and causing a interference pattern on the detector, right? Where I have most intensity at 50 degrees, but no intensity over here and little intensity to the right, which is pretty interesting. Okay. And so in 1961, Claus Johnson finally was able to do a double slit experiment with an electron beam. No one had done it before then, right? It was postulated that it was possible, but no one had done it. But Claus made it a reality. Me and Claus go way back. All right, so what's the game here, right? If the electron is ultimately just a particle, when the electron gun shoots out my electrons, they're going to come out at random angles, right? And if it's passing through my two slits and they're coming out at random angles, well, it's going to hit the back screen and it's just going to give you two lines because all the ones that come off at too high an angle get reflected, and the other ones will just pass through and they'll hit that back screen. So that's what will happen if it's a particle. But if it's a wave, when you shoot it through, you would end up seeing a diffraction, or not diffraction, but a interference pattern on the back. So this would just be some diffraction pattern, and this is actually an interference pattern. Oh, pretty interesting, right? And so if you look at the experimental images of this, right? So here's the experimental images of a real screen on the background. As you start shooting them through, you get some dots popping up and then more dots, and then you see voids in between these really intense lines, right? And this is where there is constructive interference, and then where there's the dark, that's destructive interference of the wavefront associated with our particle hitting this screen that's in the back. It's pretty wild, right? Okay, so 1961, Claus Johnson figures this out and actually makes it a reality and proves, look, the electron is a particle, but it has wave properties, so it's a wavicle. So now, with that in mind, experimenters thought, hey, look, there's some funny business going on here. Let's just look and see which slit the electron went through, and then we'll be able to tell more about what's going on here. So the game is if you place a detector before or after the slits, right? If I place it in front of the slits or after the slits, so as to know which slit the electron or photon went through, the wave-like nature of the particle collapses. That is, it becomes a particle, just a bit of mass flying through space then. And one only sees two lines in accordance with the particle-like activity. So if I put a detector here, or I put a detector there, doesn't matter, in front of or behind it, and I fire my electrons, and I detect which slit it went through, well, then I'm going to see two lines. It's going to act exactly like a particle. Well, that's pretty wild. Okay. And then we're going to go and we're going to say, all right, it seems like the act of a conscious agent observing the particle causes the particle to choose one slit or the other slit, and not to exist in a superposition of going through both slits as it does when it's acting like a wave. So if there's no observer, meaning there's no one perturbing that wave function as it passes through those slits, it just acts as a wave. But as soon as there's any perturbation of that wave function, right, by an observer, and that observer can be you, or it could be a cat, it could be a plant, it could be a rock, it could be a computer that's monitoring it, the wave function collapses. It's forced to choose. And the superposition of going through both becomes just a position of going through one. I don't know. That's just what it is. Okay. So, what's even weirder, though, is if you erase the information about what slit the particle passed through, you get an interference pattern again, not a pair of diffraction patterns. What the hell? Right? So, if you pull away whatever's detecting it, right? Like I have the same experiment, right? And I'm detecting it, I get a diffraction pattern like this. I pull away the detector, I end up with an interference pattern immediately after. What kind of sense does that make? I'm shooting the same electrons, but the act of observing, right, or the act of engagement with the wave function by another conscious agent causes the wave function to collapse into one of two states. Very, very bizarre. So we can look at such an experiment. So here's the experiment. My electron beam is coming through a slit here and is going through a double slit there. And I have this square that I can move from side to side. Yeah. And this square can tell me if I'm blocking the left slit or if I'm blocking the right slit, right? And so if we play this game down here, if I come down here and what we're looking at is we're looking at this thing sliding in front of the slits. So as one slit's open, I see a diffraction pattern. As two slits are open, I see the interference pattern. If I block the other slit, then now I have a diffraction pattern. And then, like, how is that even possible, right? I'm blocking one slit, diffraction pattern. I open up both slits where I don't know if I'm going through slit 1 or slit 2. I get an interference pattern. I close the other slit, back to diffraction pattern. What in the world? If you were to watch this in real time, you know, we're firing electrons one at a time, one at a time, one at a time, and they start to appear on the background, right? You'll get a fluorescent blip. So you're using a fluorescent background and you excite that fluorescent background and you end up seeing a blip where the electron hit. And over time, if you just keep shooting electrons, you'll see that an interference pattern shows up on that background. And that is just absolutely mind-blowing to me. I mean, I'm shooting particles, and you can see one particle's hitting at a time, but over an extended amount of time, the pattern that emerges is a freaking interference pattern, not just a standard diffraction pattern if there was no interaction of the electron with itself as it passed through the two slits. What? I don't know, man. The matrix that we're living in is pretty interesting. All right. So let's go forward and try to understand some more stuff here. All right. This brings us to something called the delayed choice quantum eraser. This is going to blow your mind. What in the world is this? So Scully et al., so the Scully group, makes the following quantum eraser and demonstrates non-locality of quantum particles. So this was done in 1999, so the paper's pretty new. And so what's locality and non-locality? So locality says that objects must be in the vicinity of one another in space and in time to cause an effect, right? So it makes sense. If I want to lift up my hand, or if I want to lift up my shirt, my hand's got to be next to my shirt to lift it up, right? locality. It's got to be in the same location to make that happen. All right. But it turns out that quantum particles have non-locality. That is, objects need not have space-time coincidence to cause effect on one another. What in the world? Okay, so let's look at this experiment. This is really, really cool experiment they did. So what they did is they took an argon laser and they fire it at a double slit. All right, so it's a pulsed laser and they're firing approximately one photon at a time. And we don't know if the photon's going through slit, this is going to be slit B or slit A, right? So it's going to go through one of two slits. All right, and so they shoot this laser, this pulsed laser, at this double slit, and what it does is a photon's going to go through either slit A or slit B, and it's going to hit this beta BBO crystal, where BBO is barium borate crystal. The laser goes through and it hits this barium borate crystal in one of two regions, right? It either hits it right here if it goes through A, or it hits it right there if it goes through B. Okay, and so now we don't know if it went through slit A or slit B. And what happens is this photon gets absorbed by the BBO crystal. And so this 351 nanometer photon gets absorbed. It's a high energy photon. And what happens is you get spontaneous parametric down conversion of that photon into two triplet photons, each having an energy of 702 nanometers. And now these two photons that get produced from the down conversion are going to be entangled. And they're going to be entangled because they came from one photon, right? One photon went in, excited an electron. When that electron decayed down, it gave off two photons of the same frequency. And now, since that happened at the same time, those two photons are now entangled with one another because they came from one source. Okay, whatever you say, Dr. Bo. So let's look at an image of this to the right-hand side. So here is your incoming photon. It strikes one of the lattice sites in the BBO. Upon doing that, our electron goes from the ground state to the excited state, and it decays via this spontaneous parametric down conversion, and it gives off a photon and a photon, bang bang, at the same time. So photon 1 comes off, photon 2 comes off. All right, and now these two photons are entangled, but they have different polarizations. So one will be polarized vertically, right? So the plane wave will be orientated vertically. But by the constraints of entanglement, the other photon must be polarized horizontally, right? So its plane wave is perpendicular to this plane wave. So this vertical one, we'll just call the vertical, or the idler. The horizontal one's the idler photon, and the vertical one is going to be a different photon that we're going to describe momentarily. Okay, it's called the signal photon. So the vertical one's the signal photon. The horizontally polarized one is the idler photon. Okay, and so how that works is our laser shoots the BBO crystal, and then our two photons come off. One will be polarized vertically, one will be polarized horizontally, right? And here's another picture of our two photons coming off after our incident photon struck our lattice site. All right, so hopefully everyone is on board still, right? Firing a laser, it's a pulsed laser, individual photons, either goes through slit 1 or slit 2, hits region A or region B, and then when it down converts, it's going to split off a pair of triplet photons of similar energy that are entangled. Now, only about 1 in 100 million conversion processes or down conversion processes result in this coupled photon uh, instance. So when detection happens at our detectors, it's essentially one photon at a time that we're detecting. It's not a constant barrage of photons with respect to time where multiple photons are hitting the detector at the same time. All right. So now we're going to move forward and try to understand this experiment some more. So I go ahead and I have my two photons coming off here, or I have my two photons coming off here, depending on where it's struck on my crystal. Now, there's something called the Gland-Thompson prism right here that's going to send the vertically polarized photon up to D0, and it's going to send the horizontally polarized photon down to this prism down here, PS. All right. So the one that goes up is called the signal photon, right? The vertically polarized one that gets shot up to D0 is called the signal photon. The one that goes to the prism is going to be called the idler photon. Okay, so that's just what they're called. Now, if a photon passes through slit B, because this will be slit B, it's going to go and hit this prism, and then it's going to hit this beam splitter B. Now the beam splitter is going to send 50% of the photons up, and it will transmit 50% of the photons. Same thing for if I'm coming from region A, it'll hit the prism, get deflected to beam splitter A instead of beam splitter B. 50% will go to D3, the detector D3, and 50% will pass through to this mirror. Okay, so far we're getting what's going on. Idler photons go down, signal photons go up. They're entangled, meaning they're linked together because they came from one source. Okay. And so if a photon passes through slit A, it'll be reflected to the prism. It'll hit beam splitter A. Half goes up, half goes down, like I just described. So now what does that mean now? Now what we're going to do is we're going to focus on these detectors. We're going to focus on detector D3 and D4. And we're going to turn off detector D2 and D1. Now, if I only leave on these detectors, then I know what slit my photon came through, don't I? Right? If it hits D3, I know it came through slit A. If it hits D4, I know it came through slit B. Yeah? Okay. So if I now know what slit it came through, right? What do you think? What pattern do you think I'll see on DO? Will I see an interference pattern or a diffraction pattern on DO? Well, it turns out I'm going to see a diffraction pattern, right? Because it's acting like a particle, because I know how the particle had to act and where it came from. Now, here's what's super crazy about this. There's an 8 nanosecond delay between when the photon hits D0 and when it hits D4. I don't know if that's blown your mind yet. There's an 8 nanosecond delay. But this photon here knows that this one is going to be detected as to which slit it went through, and that the wave function must have been collapsed after it hit that detector. And so through time and space, it travels back in time, tells this signal photon that it got detected over here, and makes it form a diffraction pattern. What? I don't know. Super crazy. So the act of observing where that photon went allows you to effectively time travel, right? These things are entangled. 8 nanosecond difference. This one ends up somehow communicating to this one that it got detected. And it got detected which slit it went through. Whoa. Okay, really, really crazy. So now we go back and we think to ourselves, well, we know that the photon really passed through both slits, but it only excited in one spot. And once it got detected what slit that it excited at, then it ends up making this diffraction pattern. Oh, wow, that's really crazy. It's acting like a particle, right? Our photon is acting like a particle. So this describes this idea of non-locality. That is, this photon isn't in contact with this one in time or in space, but it has an effect on what appears on the detected surface in the background. So you just get these diffraction patterns as a result of hitting these two detectors. Whoa. Now it gets even weirder, if it can get any weirder. So now imagine that I turn off detectors D4 and D3, and I turn on detectors D1 and D2. Now, why does that matter? Well, if I go from region B and my photon's emitted from there, hits this prism, goes through the beam splitter instead of being reflected up to D4, goes through the beam splitter, hits this mirror, then 50% of my photons that pass through this beam splitter will go straight to D1, and the other 50% will go up and hit D2. Okay. Now I do the same thing for coming from region A. Hits the prism, goes through the beam splitter, hits off mirror A. 50% gets reflected off the beam splitter, 50% passes through the beam splitter, and goes to D1 or D2. Now, in this instance, there's no path information given to me because it could have come from this photon that's hitting at D2 could have come from region A or it could have come from region B, right? They're both hitting the same detector. Same with detector 1. It could have come from region A or it could have come from region B. So I don't know what slit or what region got excited, do I? Okay. So if that's the case, what pattern do you think I see at D0? Do I see an interference pattern or do I see a diffraction pattern? Turns out I see an interference pattern because it's acting like a wave because I didn't make the freaking photon choose which hole it went through. It went through both holes. It excited both regions and passed through according to the wavefront in the photon, right? Clearly it had to have hit one of the goddamn regions, but you don't know which one it hit. And so it plays the game and just gives you an interference pattern and doesn't tell you which one it hit. What? Okay. So if we go ahead and we look at the outputs as a result of striking D1 or D2, you end up seeing an interference pattern, right? We can see that there's regions of highest intensity as a function of interference of the wavefront associated with the photon. And that's only because I didn't collapse the wave function by knowing which slit it went through. It pops my brain talking about it. Okay, so the act of knowing, the act of being a conscious agent or a conscious observer makes quantized materials choose to be a particle, right? Or act like a particle. And that might be because of the interface that we have. We only understand matter interactions. We can calculate energetic interactions, but we don't know what it is. You can't grab energy. You can't take energy and hold it, right? Our brains and our fitness goals aren't that aligned with those of energy, so we don't perceive energy that well, right? Okay, so we're going to move forward with this. So some argue that the detector is causing an influence on the particle states, but And that really appears to be the case when you're talking about D3 and D4, right? Because you get an interference pattern. But when you have D1 and D2, and you get we had a diffraction pattern when we had D4 and D3, but when you have D2 and D1 and you end up with an interference pattern, the detectors aren't doing anything, right? They're just detecting that something hit it, and we're shooting essentially one photon at a time. So you'll see dot by dot by dot pop up as the photons hit the screen, but it makes an interference pattern because the photons are interfering with their cells, and they are in the superposition of all states possible to the system at any time until you observe it. And all a superposition of states is the possible states that the thing can exist in, all combined into one wave function. And we're going to deal with that in great detail later. So this is remarkable because it shows that a single photon knows what happened to the idler photon 8 seconds later, or 8 nanoseconds later. Or it already knew what would happen to the idler photon before it left. So that's even a crazier idea. When that photon, that entangled thing, left the other one, it knew what was going to happen to that one before it ever happened to it, right? It either saw into the future, or the other one went back in time and told the other one what was going to happen. What? Pretty interesting, right? Pretty interesting experiment. All right, so overall, what does the delayed choice quantum eraser tell us in its weirdness? So it appears as if time travel has occurred. That is, the signal photon doesn't reveal its state until it is informed as to the detected nature of the idler photon. At that point, it matches the idler's state though detected previously in time, right? Because the signal photon got detected first, then the idler photon. But its answer will be based on whatever happened to the idler photon. So either it's a particle or it's a wave based on what happened. So according to the Copenhagen interpretation of quantum mechanics, the particle remains in the superposition of states, that is, as a wavicle until it's observed. If observed, the wave function describing the probabilistic nature of the particle ends up collapsing, and the particle appears to take on a deterministic nature. That is, it becomes more particle-like than wave-like. So it seems like we, being the observer, have an influence over how the particle exists. And now, don't get your ego in a spot where you think, oh, yes, me, I'm the observer, I matter, because I'm unique, I'm this thing that perturbs space and time and matter. No, anything's an observer, right? Notice that all these experiments were run in vacuum, so nothing influenced the particles that were flying through the air. Well, there is no air, but we're flying through the void. As soon as you stick something in there and the particle interacts with it, well, then the wave function collapses and it acts like a particle, right? So anything's an observer, right? Anything that interacts with other matter is a conscious agent, and it influences that other thing. All right, so the particles are always existing as a wavicle. This is a problem. Particle is always a wavicle. It's just that our user interface makes us choose the state of the particle, right? Either it went through that slit or that slit, and our user interface, the way we interact with the world, makes us choose one or the other so that we can make a decision to obtain a fitness outcome, right? And when we want to observe the particle directly, we resort to deterministic mechanics because that's how our user interface works. We want to know, did it go through slit 1 or slit 2? Not, oh, it went through both slits and it's this, superposition of possibilities that's existing everywhere. No, we want to know where is it and what's the highest probability of where it's going to be so I could use it for some fitness outcome, whether that is to get food or to mate or to kill my rival. We want to know, where did it go? What did it do? All right, so let's look at we got 2 more slides here. Let's look at at another way to try to understand this. So we're going to look at entanglement in conscious agents, right? So here's a Necker cube, right? This is called a Necker cube. And it's got two states, according to your eyes. It's got state one, where, we're looking at it this way and I could jump on top of this box right here. Or I got state two, where to jump on top of the box, I got to jump at it at a weird angle, right? But it's the same exact representation as this thing, but it's just drawn two different ways, right? But it's the same, it's drawn exactly the same. Like the lines are, this would fit exactly over that, this would fit exactly over that. This Necker cube exists in a superposition of two states. But when you look at that Necker cube, your brain's got to decide, is it this orientation or is it this orientation? And which one am I going to deal with, right? Because if I have to get over this cube or get around this cube, I got to know how to deal with that shape. And so your mind collapses the superposition of two states into one of two states. Okay. So we know it exists in a superposition of states, but your user interface is going to make you choose which one of the simultaneously existing states you're going to deal with, and then you solve the problem that you're trying to solve from there. So when you're not looking, how does that box exist? Does it exist like this or like that? Or is it the superposition of both of those? Well, most would argue that, that deal with conscious agent theory, that it exists in a superposition of two states, and you make a selection to move forward. And all matter does this. All matter, when it encounters whether it's photons or electrons or everything else, makes the choice as to how it's going to experience those things or how it's going to perceive them, which is a super crazy idea, right? But it's kind of how we have to think of things. All right, so if I was to write a wave function that could describe the true state of the box, it would include both possible states. It would include state one and state two that are normalized, right? So this is a normalization coefficient that makes it just as likely to be in state one as it does to be in state two. And that the overall wave function is the sum of the probabilities of being in either one of those states. Okay. And so now let's look at this idea of entanglement and the conscious agent. So now we have this Necker cube, and we're going to do this spontaneous down conversion. We're gonna mimic it with this Necker cube. So the two different color lines represent the vertical and horizontal polarizations of our photons that came off. So we could say this is vertical and this is horizontal polarization. And now I can assign the color of those two things to two different states as well, right? I could say this is one way that it could be represented, right? The photon 1 is vertical, photon 2 is horizontal, or photon 1 is horizontal and photon 2 is vertical. Okay, but which one's correct? Well, they're both the same, right? They're both have the same probability of existing, and so they exist in a superposition of two states, right? There's a wave function that exists that describes state one. There's a wave function that describes state two. And these are probabilistic representations of how often you would see either one of them, and they are equally as probable. But your brain or the detector or the computer has to choose one or the other if I know the path information. What? Super crazy, right? So whenever the red is near and the green is far, and vice versa, right? This model is the same as type 2 spontaneous down conversion, and it models it perfectly. And so we can then write a complete wave function as a superposition of states, right, of those two things. And the problem then of mixed states isn't reality's problem, right? This problem of the wavical nature of particles isn't reality's problem. It's your problem, because your user interface is forcing you to choose, oh, you're acting like a particle or you're acting like a wave, not that you're a wavicle and you are both these things and you exist in a wave function of probabilities that you could be anything, right? You ultimately collapse your wave function to one thing so that you understand it. It's kind of how you view your life in general as well, right? You have an infinite potential. You have infinite number of possibilities, but you ultimately collapse down to this one vision of yourself. Oh, grasshopper. All right, so we're going to leave it there and we'll pick up with some other fairly standard experiments next time. I hope you enjoyed that. This is really why I love quantum. All right, talk to you later.